Okay, welcome back. What I want to talk about next is the simplest model of the atom, which will ultimately allow us to understand how photons of or quanta of light or photons are absorbed or emitted by atoms and molecules. And so to do that, we're going to use kind of the most celebrated simple model of the atom, called the Bohr model. Bohr model of the atom, of course, with which you're all familiar. Um, Before we do that, there is a quantity that I would like to discuss that will allow us to make sense of the Bohr model. And this quantity is usually not something that the chemist encounters frequently, particularly in kind of through general chemistry and organic chemistry and so on. That quantity is called the action. So the action has a specific physical meaning, as opposed to the colloquial use of the word action in our daily life. And so that's what I want to talk about. And specifically, what I want to consider is the motion of a particle around a circle. So circular motion. And so imagine we have this kind of a circumstance. We have a circle, and you have a particle that is moving along the circle with some speed v. Particle moves around circle with speed v, and the radius of the circle we're going to call r. And the particle has mass m. Just we give, I shouldn't, let me do fewer arrows. This is indicating that this point particle is moving around the circle. Here's how the quantity action is defined. As the particle moves an infinitesimal distance along the circle that we're going to call ds, the change in the variable action looks like this. The infinitesimal change in the action A is going to be equal to the momentum of the particle times the distance that it traveled along the circle. So if the particle travels an infinitesimal distance ds along the circumference of the circle, the change in that function called action is going to be equal to the momentum with which the particle is traveling times this infinitesimal distance ds. And this is going to be equal to m, the speed with which the particle is moving, times ds. Now, if you have a circle, a small length ds can be related to the angle through which the particle moved as it traveled ds and the radius r. In this case, ds is equal to r d theta. And so actually, instead of calling this theta, let's call this angle infinitesimal angle d theta. This makes sense because if you can think about this, the length of the circumference of the circle is 2 pi r. In the length of the circumference 2 pi r, the angle undergoes one revolution of 2 pi radians. And so this kind of a connection makes sense. Nevertheless, this is what it is. And so we can go here and we can say the infinitesimal change in the function a, the action, is going to look like m v r d theta. As the particle executes one full revolution around the circle, the value of the action is going to be equal to the integral from angle equals 0 to 2 pi, so a full revolution around the circle, if we call this 0, m v r d theta. The mass of the particle is fixed. The speed with which it's moving, as we stipulated in the problem, is fixed, as is the radius. And so all these terms are constants with respect to integration over the angle. So they can come outside the integral. And so what this is going to look like is mvr integral from 0 to 2 pi of d theta. The integral just gives 2 pi minus 0, which is 2 pi. And so this is 2 pi mvr. And so the action of a particle that moves around the circle, as we defined it, is going to be equal to 2 pi mvr, or this is its mass, this is its speed, this is the radius of the circle along which it's moving. So the larger the radius of the circle, the larger the action for a given mass and speed. And for a given mass and radius of the circle, the faster the speed, the larger the action. You may or may not have encountered in your physics classes, probably may have, likely did encounter, the idea of the angular momentum. The angular momentum magnitude, angular momentum is a vector, so it has a direction and a magnitude. The magnitude of the angular momentum vector is a quantity that is extremely important in rotation of any kind. The angular momentum magnitude we're going to call L is equal to mvr for the particle that moves around the circle with a constant speed v. Therefore, the action is equal to 2 pi times the angular momentum, as you can see by comparing these two equations. And so, in a sense, it looks like we haven't really done anything important. We've just simply multiplied the angular momentum by 2 pi and, created a new function out of nowhere. But it turns out that the function action is actually extremely important in all of physics, and therefore in all of physical chemistry, and therefore all of chemistry. Insofar as physical chemistry underpins all of chemistry as its very foundation. And so there's going to be a reason that we'll see that the action pops up in the treatment of the atom by Bohr. And so that's what we're going to do next. But so far, all I wanted to do is just introduce the idea, the definition of the function A, the action, and so on. And so the action A is often associated with periodic motion, or is often comes up in periodic motion, where it doesn't have to be particle on a ring. There are other circumstances where the action concept is applicable, but for us, we just need to think about a particle moving on a ring with an eye towards electrons moving in the orbit of a proton, effectively.